Okay, hello everybody. My name is Brighten Godfrey. I'm co-founder and CTO of Veriflow, and I'm very happy to be here. This is, I guess, a busy week for product announcements. So apologies to Apple that we're kind of upstaging them. But we're really excited to be announcing this technology and telling you a little bit about it because it's it's some work that we're really proud of by an incredible team, and I'm lucky to be able to be the one to tell you a little bit about it. So let me actually first mention a little bit about myself. So I was a PhD student at Berkeley where I met Matt. I worked with Jan Stojka, he was my PhD advisor. Took a job as a professor at the University of Illinois, where Matt and I met Ahmed Khurshid, the third co-founder, who, the three of us together, began pioneering this area of network verification that a few years later became the company. And as an academic learning about network engineering for the first time, something that struck me was, wow, these networks for large enterprises are really pretty complex. Right? And thousands of devices, layers of technology, actually increasing layers of technology. You think about SDN and cloud layered on top of what you already had to do. They help automate in some ways, but they also can obscure and add new layers of complexity to the system. So it's a pretty daunting task. It's, in one sense, it's pretty impressive that, people can work with these technologies, but in another sense, it is, a very difficult thing to do, given how critical these networks are. And let's just put some numbers on it a little bit. This is a survey from last fall. 59% of IT professionals that were surveyed here said that the growth in complexity in the network actually did lead to more frequent outages. And later on top of that complexity is this change, which can be hundreds or even thousands of changes per month in an enterprise. This number here is from DISA, 22,000 changes per month in a very large network. And so you have a complex system being continually changed by largely manual processes. And this, again, surprised me as someone coming out of computer science and learning about network engineering, that the tools that network engineers have to deal with are still typically manual. So 69% say that the way that they verify the network is functioning correctly is actually using manual checks. That's like pings, trace routes, going to a service, seeing if it works, that sort of thing. Now, that, of course, gives you no guarantees whatsoever. The other thing you can do is monitor. Watch samples of user traffic or events after the fact, right? So that's, with monitoring, you're only seeing problems after they're already affecting users, or even worse, after an attacker is already exploiting a flaw and exfiltrating data or something like that, okay? And there's homegrown scripts and so on. But basically, this is not a very good situation, right? We're trying to manage a system that's become very complex. Really, if you think about it, and modern enterprise network is at the level of complexity of kind of building a distributed software application for the whole enterprise, right? This whole collection of products and scripts and so on, working all together to achieve a single purpose. So we need really better technology to deal with that. And when Ahmed and Matt and I were thinking about this, we looked to other industries, as Jim mentioned, that need to build complex engineering artifacts. And there's this concept of formal verification, mathematically analyzing a design before it's deployed, that's been very successfully applied in some industries. NASA, for example, uses formal verification in the flight software for their Mars rovers. So I'm not sure if you saw the movie The Martian, but little spoiler, Matt Damon is stuck on Mars. And at one point has to dust off the old rover and turn it on to communicate back home. And that's kind of representative because these systems are actually quite reliable. So the exciting thing is that we are applying formal verification to networking for the first time. So let's kind of dig into the technology here. So let's first clearly define what is network verification. This is the process of proving whether the network meets the goal. That's basically what it is. What do we mean by the goal? Well, that can be something high level, like my data center should be resilient, or this critical service in my data center should be available to every one of my remote sites, each one of my hospitals maybe. None of my users should be able to access the internet except through a firewall. So these are end-to-end goals. I'm not talking about VLAN IDs or IP prefixes or that sort of thing. I'm talking about what I want the network to achieve end-to-end, and I want to be able to verify that rigorously. Okay? So how do we do that? So Jim showed you this, this 3-step process here, and anything that has 3 steps is easy, right? So, but actually, there's some significant technical challenges in each one of these steps, and that's what I'm going to dig in and tell you a little bit about. The first step is collecting that data plane state from the network. And as Jim mentioned, we're working with layers 1 through 4 devices, physical, also virtual, routers, switches, load balancers, firewalls, access points. The effect of a network, the effect that the network has on processing traffic flowing through it, is really a combination of configurations, millions of lines of vendor code, protocol state, forwarding state, and then the physical components themselves, all working together. One thing I want to emphasize, though, is that it's really not enough to only look at the config if you are, if you want full accuracy. Now, I'll give you a practical example from a customer that we're working with, a large Fortune 500 financial, where, like many enterprises, they frequently update their router software, right, and across many devices. And when you do that software update, you want to actually ensure that the behavior has not changed. So the config is the same, but maybe something changed in the network. Maybe the vendor changed the way some knob or dial subtly interprets something, or it converged differently, or something didn't get pushed out correctly. Whatever it may be, pretty frequently there's a good chance something goes wrong. So you want to be able to verify if that behavior is actually the same. So that's a practical example. So while we look at many parts of the network, kind of the core of the model that we build is extracting that data plane state. So I wanted to emphasize that. Now, the problem is actually even harder because of the diversity of devices out there in the world, devices and protocols. Many different vendors, maybe dozens of different vendors and protocols, all trying to work together. So this is fundamentally a multi-vendor, multi-technology problem. So what we do is we take the data plane state from each of those devices and we convert it into a single abstraction. We normalize it so that all of those devices, everything from like that, that old Cisco box that hasn't been rebooted in 10 years, and literally we see this in customers sometimes, all the way to an Amazon VPC that you just spun up a couple minutes ago in a single abstraction of the functional behavior. And that's already a very powerful thing because it's cutting through the first part of that complexity. Now, once we have that model, or that normalized kind of raw input data, then we can build this network-wide predictive model. And here we're reasoning about the whole network as one system, not device by device. What I want to emphasize here is that this is not monitoring. We're not looking at past traffic flowing through the network or ongoing traffic. We're not tapping ports or looking at net flow. We're not looking at a single user data packet flowing through the network at all. What we're doing is we're predicting all possible data flow that could occur through the network.
So you're effectively taking routing table, ARP table, MAC table, echoes, and then using this sort of static information, if you wish, you're predicting how, based on these entries, the traffic could flow through the network.
That's correct.
Okay.
That's right. Yep.
So a lot of state is ephemeral. It's not derived from the configuration. You really need to understand the context of the ephemeral data presented at a particular moment. How do you normalize it across different devices which have very different representation in general?
Right. So I guess there's two questions there. There's the ephemeral nature. There's the fact that the state is changing frequently, and then the normalization across different kinds of protocols and devices.
Yeah. So it's three questions.
At least, the more the better. That's what we're here for. State is ephemeral, and you're right that it can't be entirely derived from the config. So that's why it's important to get that lower level state. Basically, the data plane is as close as it's practical to get to the functional behavior of the device. So when a packet goes into the box, it's going to go through this decision procedure to decide what to do with it, whether to send it out port 23 or stuff it in this tunnel or modify it or drop it on the floor. So we know what its decision procedure is.
Does that mean that you know peculiarities of different data planes, including
including DMVPN? Just ask it.
Yeah. So many are
TMP hashing capabilities, or the size of ACL tables, or things like that.
So there are many peculiarities that our team has become very familiar with.
I bet.
So do you have like 50
you
gajillion
aspire to include all of that, or is this just like routing tables?
I think we're not modeling kind of maximum table sizes in terms of folding it into the model, although that's information that we pull, and it's there, and you can query it. There's issues like, in what sequence does a device actually execute operations within it? Because there's a whole pipeline within the switch, right? It's not just one node.
Sure.
It's doing a lot of different things, even if it's a switch, and then it might be a firewall or something else. So you have to understand, and in some cases this takes some reverse engineering, exactly what that device is doing. And then you have to deal with the fact that the way that you're collecting data is often not through an API. It's through often SSH over the command line, because that's the least common denominator, and it's formatted in a way that's not documented, and might have various peculiarities in just to parse it, right?
Sure.
So there's a whole breadth here, but that's a little bit of the scope of it. So it is a lot of work to be able to build these device adapters for a whole range of different kinds of devices, to be able to represent all those devices and this whole matrix of devices times protocols, basically, in one format.
Well,
Sorry.
No, I was going to ask you, will customers build their own data to pull these data from unique devices and that you don't support?
That's a good question. Yeah, so we do all that ourselves. We take care of it. Now, we already support a broad range of devices and protocols. We're always adding more and more, and we can do that pretty quickly if there is something that the customer needs, and we have a team that does that exactly. In the future, it is possible that there's this abstraction layer that we could open up as an API to make more open for people to program parsers and device adapters themselves. We haven't done that right now. It's a little early, but there's definitely the possibility of that. Yeah.
You stated you're not looking at load state of the device. Is it correct?
I'm sorry, we're not looking
Are
at...
you looking at load of particular interface, flow per interface, state with regards to the amount of traffic passing?
So we pull a variety of interface properties, like statistics, and does it have a lot of CRC errors, that sort of thing. We're not really looking at like real-time traffic flow on the interface.
My question is, what you're trying to do, you're taking your configuration or state as is, you're taking the future state, and you're trying to figure out what needs to be applied to get there. However, as you change your configuration, your distribution of traffic is going to change. So you might overload another interface. Very common thing.
Yeah, that's possible. Yeah.
So if you don't know the load, how would you encounter?
Yeah. Okay. So that's a good question. So I guess the question to summarize is: do we have an understanding of the traffic matrix, the matrix of utilization overall, so we can see how that will be adapted, how it will evolve with changes to the network, or how it would be affected by some problem? Today, we're not collecting information about traffic matrices and traffic flow patterns. the focus is just more on preventing outages and vulnerabilities. But because we have this network-wide model, there's absolutely the opportunity to do that kind of thing. And we have an API, and actually you could program to it today to say, OK, let me run these scenarios. Let me see what different traffic matrices would do in the network. So we have kind of the raw ability to do that, but it's hasn't been the focus of the product to date.
Okay.
Well, just one more question.
So one of your marketing messages is we can predict what the changes will do. Okay? So what you're doing now is you told us you collect the state. You can analyze what is going on now. You can predict whether the flow would go from A to B.
That's right.
As I introduce the change into the network with all the bugs that are there in network devices, how can you predict what impact this change will have in my network? Because you can't collect the state because I want to verify the change before you have the ability to collect the new state, because by then my network is down.
Right, yes. So there's two kinds of prediction. Great question, thank you for asking. By collecting the live data plane state, we can predict how traffic will flow through the network. So basically, you don't have to wait for monitoring, right? And this is a huge benefit. One of the features that we're announcing today, which is pre-flight, then goes a step further and says, let me start with the configuration change and predict how that will affect the data plane. And then it goes through the rest of the product. Okay? Now, our pre-flight capability that we're announcing today is for access control changes, which does limit the scope of
Okay,
what
that
we have.
severely limits the scope. Yeah,
Yeah,
that's
right,
the easy part.
But as you'll see, even with those kinds of changes, being able to formally verify everything that could happen in the network is, a huge value. And let's look at the scope of kind of the life cycle here. There's the design phase, where you're planning a change, and that's where you'll use pre-flight. Then there's the implementation, where you need to know, okay, did that actually get implemented correctly in the live network? And I want to know very accurately. And then there's operation, where I'm not making any changes explicitly, but something may happen. Somebody else injects something into the network, or there's a interface failure or something like that. So, at those different phases, in the design phase, you use pre-flight. Throughout implementation and operation, you use kind of this core data plane verification from the live snapshots of the network, so you can get high accuracy.
So effectively, you can answer a question that one of my friends was trying to solve on his own, which is, if this client can't get to this server, can you please show me which echoes it's hitting on the way?
That's an example of a question we can answer, yes, very easily. And you'll see examples like that in the demo.
That's cool.
Mm-hmm. Yep. Yes?
Are you able to verify configuration versus operational state? So if I have an echo, and it's configuration, but guess what? It's not filtering anything, because there's inconsistency between forwarding plane and control plane. Are you able to see this discrepancy between configuration and the forwarding state?
Yes, we would be able to do that. So that's the kind of thing.
If the inconsistency shows in the show printouts. If there's a TCAM problem, you can't detect it.
If we can extract the actual state from the device, then we'll be able to see it and compare. Yes.
How often is all of this running? Like, how often are you querying? Because obviously at some amount of scale, that's going to be ridiculous.
That's configurable. Yeah, that's configurable. So you might run it once a night, once an hour, but also as you're making changes, you'll do a pull.
Right, okay.
So I think what I'll do is I'll get through a couple more steps here and then take a few more questions. So when we, let's review where are we so far. We collected this data plane state from the network, and now we're building this predictive model, which is looking at all possible traffic that could happen in the future, right? And that's a lot of possibilities, right? If you think about it, let's just take a simple case. Imagine we only had to model the layer 2 and layer 3 Ethernet and IPv4 headers. That's 18 bytes plus 20 bytes. It's the number of possible packets is exponential in the number of bits in the network. In that header, excuse me. And then let's say you can inject it at 10,000 ports in the network. So this is about 10 to the 95 theoretical possibilities that you could inject packets into the network. And just to put that in context, that's about 10 to the 95, even under moderate assumptions. The number of ants on Earth is about 10 to the 16, and the number of atoms in the observable universe is about 10 to the 80.
And that's the argument of monkeys typing Shakespeare. Can we move on?
Exactly. So we're not going to be able to simulate one packet at a time. This is not a simulation. That's where formal methods algorithms come in to be able to analyze the network. What we've done is in our original research papers, and one of them was Ahmed's PhD thesis, we've developed techniques based on formal verification for networks, using concepts like what we call equivalence classes that determine signatures of traffic that provably are going to have the same behavior throughout the network. So what that means is our model is not just the physical model of the network. There's a whole other dimension to it that reasons about everything that could happen in a graph-based model where these nodes are what we call flow nodes that represent a signature of packets at a certain location. And we build this overall graph-based model of all possible functional behavior. So it's basically a custom graph database that then you can query and ask questions about. Okay, that's modeling all possible behavior in the network. Anybody see any problem in this?
Yes.
It's NP complete.
It's at least NP complete. Yes.
If you have all the data, you could do it in software. How do you derive all the data? There's price associated with keying every flow, signaturing it, exporting all the information to your software layer. And not every NPU will give you the ability to do so at line rate.
Right. So that's a great question. So basically the question is, how much volume of data do we need to collect from the network, and how do we deal with that? And it's actually not that much. It's about 1, maybe 2 megabytes per device for a snapshot. Because we're not collecting live traffic from the network. We're not collecting any traffic that's live flowing through the network. It's just the state on the device, which means like forwarding tables, ACLs, MPLS tables, layer 2 information, and so on. So it's relatively limited.
So effectively, you start with a simple graph, which is just a forwarding graph. Mm-hmm. And then you add ACLs to that, and ACLs segment the traffic into equivalence classes.
That's right.
And then you have the Cartesian product problem, because different ACLs multiply the number of equivalence classes. Yeah. Mm-hmm. And in the end, you get to the point where you have these tiny micro equivalence classes, which are mapped to paths across the network, and you can query that.
That's right. Yeah, and they may be graphs, not explicitly paths. So, for example, you may have cases where there's load balancing, so it fans out or can fan in some. So, that's the right idea. And then it's not only ACLs; it's also every protocol is basically looking at bits and manipulating them in some way, and they all go into this concept of equivalence class. So, ACLs will kind of slice you up into finer and finer distinct behavior. MPLS will do that, and natting, and anything that distinguishes some packets from other packets, which is almost everything that the network does. So this is still pretty high level, but hopefully gives you a little bit of an insight into what's going on.
Okay, so having this, can I then write unit tests saying this client can get to this servers? And you will say, yes, they can, or oops, you made a mistake.
Precisely. Yeah, that's exactly the right idea. And I like what you said, unit tests, because what we're trying to do here is ultimately use this to get some sort of value out of the product for the network, which is ensuring resilience or security. And we do this all in a continuous process, what we call continuous network verification, because this is an allusion to good software engineering, where you check in code to a repo and it undergoes unit tests and integration tests and so on in a process all the way out through deployment, so that you've got this continuous assurance that the right thing is happening, right? And those kinds of methodologies in software, that's kind of like the DevOps model of building and deploying rapid changes to software. And what we're trying to do is help networks move to basically DevOps for the network.
Are there integrations like that where you could check in a config into a repo and dynamically, let's say it's like similar to Jenkins or Travis on the software side, where that could automatically trigger a build job within your platform to then say your change will pass if you deploy it on this device in the network?
Absolutely, yeah. And we've built everything from the ground up with open APIs. Everything when we do the demo that you'll see with the UI is available via API, and many of our customers do custom integrations or work with our SEs to do that.
Are those things you would see coming in the future, like a native plugin for CI tools, as an example?
I think that sounds like a great idea. Yeah, we don't have an announcement right now, but that is absolutely the direction that we think the network should be going.
So your data model augmentable, or I need to go through you to extend it?
Okay, so I would say it's not augmentable today by the customer. It's augmentable by us. And you'll see that through the depth and breadth of what we collect in the demo. There's actually a lot of information. This is, that graph that I put up makes it look kind of clean and simple, but we extract a breadth of information out of the network, because what we found is just understanding the forwarding behavior, that's pretty cool, but it's even more impactful if you can understand, device state and operating system versions and combine these jointly to be able to ask questions. And I think that logic extends even further. If we get other kinds of information, maybe even flow information, you can combine queries and do joint queries in a way that's more than the sum of its parts. So that's, I think, a valuable direction.
So your continuous verification is really grab a snapshot of the state, model that, run the unit tests, report the inconsistencies.
Yes.
Repeat every whatever interval.
That's right. That's the basic process.
Okay.
Right? That's the continually, every time you're making changes, you're verifying, and now you've got this assurance.
Be part of your workflow.
Yeah, no, and you should verify this continuously, not just when you're making changes, because a change in the routing can change the path, and now you're hitting an echo you didn't hit before.
Or an interface goes down, or and things change, whatever it is.
Or there's many data centers. There's people touching data centers that you don't know about. So a change may happen, you wake up, you don't know about that change.
That never happens.
Right, of course.
No, but even before we go into changes, there are unexpected side effects of outages that no one did predict.
Yeah.
Right.
And you can not predict, you could theoretically predict them, and then you would get close to where Keradan was before Cisco bought them. Or you could just do this continuously, and when the phones start to ring, I can already go like, I know about this. There's this echo here that we'll fix.
Mm-hmm. Yeah. That's a great idea. Mm-hmm. All right, so let's talk a little bit about what this is used for. We talked about some of the technology. And one of the key uses, of course, preventing outages. And this is around really availability and resilience for the network. So imagine, you've got a simple question: is my data center resilient? I would like to know that. Everyone would like to know that. A large enterprise, would like to know that continuously about their data center. But it's actually a very hard question to answer.
Or what definition of resilience?
Right, exactly. So what does resilience mean? And we're talking about network infrastructure. You need to, if you wanted to answer that question, you would, at a minimum, you'd have to know, where your server ports are. If you have 1,000 servers, that's 1 million end-to-end paths that you'd have to reason about. Each of those you actually don't want on only a single path. You want to be able to have multiple paths that are not vulnerable to a single point of failure. And across those paths, you want some consistency, so you don't fail over and hit a stray ACL after you fail over. And this kind of thing happens pretty frequently. I think there was a Southwest Airlines outage last year where a router went down and the disaster recovery didn't work as intended. And it's a complex thing to know, right? Because you only find out about these problems typically today after you fail over and really need the resource, and then you find it's not consistent. And all of this you need to understand across thousands of different kinds of traffic, because they could all be treated maybe differently by the network. So I'm mentioning this to just illustrate the depth and breadth of what you'd have to do is far beyond what a human could really handle. Right? And so this is what we have automated through intent inference, which is one of the features that we're announcing, you'll see in the demo, to be able to automatically understand some of the structure of the network. And so it can figure out itself what the intent is, what is the goal that it should be verifying, and then to automatically verify that.
But
There's a question.
Yeah. Still, if we forget this add-on, which really generates the unit tests for me, because generating thousands of unit tests would be boring.
Cumbersome.
Yeah.
Yeah. And also,
you
often
have
people
this
just don't
graph
know.
now,
Yeah.
and effectively the question you're asking is there any subgraph of this graph where my unit tests would fail?
Yes.
So find me the subgraph of this graph under which this unit test would fail, and this is NP hard problem, I
Show me
guess.
the example.
Yeah.
It is, yes. It is.
So how much computational power do
Yeah.
you need to answer these
Right,
questions?
Right. So it is NP complete. So actually, as a slight digression, but it might be fun, if you have a network that's only composed of layer 3 routing, and you want to reason about how traffic can flow through it, this is actually polynomial time. If
Yeah,
you add,
it's SPF. Yeah, of course it's polynomial time.
if you add the ability to filter packets based on a single bit, that's all you do. Just one bit, I'm going to filter it. It's NP complete. So it is a hard problem in general. And this is where you need great algorithms to be able to do as much as possible in a complex situation. And some intuition here. There's a spectrum. There's some systems, software or networks or whatever, where it's like hello world. You can stare at it. And you can see, OK, that's definitely right. Then at the other end of the spectrum, there's this Turing complete problem, which is the holy grail of computer science of, tell me if my program has any bugs in it, which you can't solve in general. Okay? And where formal verification really has a lot of impact is kind of in the middle, in the sweet spot where it's way more complex than humans can reason about, but within the scope that computers can reason about. So, real-world networks have millions to billions of distinct behaviors, right? So that's kind of in that sweet spot, and that's kind of fundamentally why verification is an exciting technology for networks. So I think I have to move along a little bit here, but one more question.
Are you trying to re-implement all the algorithms we are using in layer 3 networking to figure out what is the shortest path, whether there's loop-free alternative to it, whether there's micro loops after, but before I recover?
That's a good question. So one advantage of pulling the data plane state is that we don't have to re-implement, all of the distributed control software, whether it's layer 2 or layer 3 protocols. We can see what the end result of the protocol. So we don't have to re-implement all that.
You don't, because you get only the best available path in the forwarding.
Yeah.
There are a variety of next ones. And you need
That's
to
true, and
understand them.
we do actually augment it with some understanding of what the alternate paths are.
So you need to look into RIP, into FIP, and into forwarding, which is a separate entity,
Yes.
and correlate all of them.
That's correct. Yep.
But it's really hard to predict what the outage will do if you're not simulating SPF, for example.
Yeah.
That's true. Yep. So the product includes some of those capabilities, and we're folding in more and more over time. Okay. So I'll just go real quick here. Another key use case is network segmentation. In many cases, many enterprises today were built with a perimeter security model where they're open in the interior, and now that's not good enough, because as soon as you're breached in one place, then everything inside the enterprise is vulnerable. So network segmentation draws these multiple layers of defense, or micro-segmentation. That can be a hard thing to do, because you've got this ball of spaghetti of a network that grew up organically over decades, and how do you know it's segmented? And then across all of those thousands of changes, how do you know that's maintained? Right? So this is what verification does, and with that predictive power, we can say there's a vulnerability there, even before a single packet has tried to exploit it, rather than waiting till after the fact. So, example of working with a real customer. This enterprise had actually segmentation zone policies written down by hand in an Excel spreadsheet. And we were able to take that and then mathematically verify that against the actual state of the network in the hardware. And that's a very strong, powerful assurance. Compliance is something that's also very manual today. Just documenting, pulling information out of the network can be very slow. Generally, sampling 5 to 10% of the network. We see that all becoming continuous, network-wide, and automated. And then finally, sometimes an incident happens, and when it does, you want to be able to respond to it quickly. You need to understand the network quickly. Whether it's somebody saying, hey, I can't get to this service, or a host that might have been compromised and you need to understand what it can reach, you need to understand the network quickly. So what we've built is a very powerful interactive search, kind of like Google Maps for your network, so you can ask questions interactively. And you'll see that more in the demo.